Okay, this week we will finish chapter 3, and let's review some figures right here. Okay, we mentioned it before. When layer 7 send message, for example, to the layer 4, and layer 4 program will segment those messages. For example, in this example, we segment the entire message into 4 segments, and the corresponding bytes is returned right there. So the first segment, the first byte of the first segment, okay, it starts from 0, the first byte, okay, to 200 byte, and the next one is 201 to 588, okay, and so on and so forth. Okay, and as we mentioned before, when we described sequence number in previous pipeline mechanism, we use the segment number, right? But actually in TCP we use the byte index to represent these segments. So for example, in this figure, the first segment is segment number 1, right? But actually it is described as this segment, its first byte is 0. Okay, so this segment will be numbered by byte 0, and the next segment, the second segment, okay, its index is 201. So we will say that this segment starts at 201 byte. Okay, it is an index, and 589, and the last one is 901. Okay, we use those bytes to index the segment received and sent. Okay, so right here, the first one, sequence numbers. Okay, those are byte streams, number of the first byte in segment's data. Okay, if you send the packet, okay, and you want to specify what is the sequence number of this segment, okay, you write the number right here, which is the first byte in segment's data. Okay, and for acknowledgement, okay, the acknowledged number is right here. Okay, it is the sequence of next byte expected from other side. So let's take this one for example. If the sender send the first packet to the receiver, and the data will be data 0, okay, and the corresponding act will be 201, because when the receiver receives the first segment, okay, its index is from 0 to 200, and its next expected data packet should be started from 201. So at this moment, the receiver will send ACK 201. Okay, and next time when the sender sends the second segment, the data will be data 201, which is corresponding to the expected number. But when the receiver receives the second segment and send ACK back, the next expected number will be 5889, because it means I already received all the byte before 589, and my next expected data will be started from 589. Okay, and so on and so forth. So for the sequence number, or sequence is the sequence number of next byte expected from the other side, and we use cumulative ACK, which is we explained it before, right? So that's it. So when you send a data packet, okay, when you send a data packet, you should write its sequence number right here. If you send an ACK packet back to the sender, you have to write your next expected sequence number, which is the acknowledged number right here. And don't forget that you should set the A bit right here to 1 to explicitly indicate that it is an egg packet. Okay, so that is. So let's take a look at this specific example. Supposedly we have two different, we have a TCP connection from A to B. We have a TCP connection between A and B. And A would like to send certain message to B and B as well. B would like to send message from B to A, okay? So first we take a look at this one. That is the first packet A sent to B. So currently the sequence number sent by A is 42, and that is the current data, okay? It has 1 byte data. So it's right here. The current sequence number is 42, and it contains only 1 byte data. So after B receives such kind of data packet, okay, the egg number should be 43, because at 42, the data is C, is only 1 byte data. So the next expecting sequence number by B is 43. So next time, when host A send the packet, let's take an example, okay? If the next packet is DEF 3 bytes, will be sent from A to B, okay? And we can expect that the packet, its sequence number is 43, and the data right here should be DEF. And we can know that the next egg number will be 46, right? Because D is the 43rd data. E will be 45th. 44, and EF will be 45th, and so the next expecting byte will be the 46th, right? That is the data sent from A to B, and we have to mention that a data sent from B to A is totally irrelevant to those numbers, because the number of byte, number of packet sent from B to A is totally relevant. So let's take a look at this one. At this moment, host B get a egg 79 from A to B. So that means A expects the next data packet will be 79. So the next packet from B to A, the sequence number will be 79. Okay, and there is a data packet. It only contains 1 byte, which is C. Okay, so at the left hand side, right here, after A receives such kind of data packet, and its sequence number is 79, and it only contains 1 byte, so the next expected number will be act 80, right? So next time when B send packet to A, the next data packet should be start from 80, no matter how many byte it will send from B to A. So basically, the sequence number used by A to B, and which is the green ones, and the sequence number and egg number used by B to A, which is the blue ones, they are totally irrelevant, because the data sent from A to B and from B to A, they have different number of packets, they have different amount of bytes sent and received, so they have different sequence number and egg numbers. Okay, that is the sequence number used by TCP. And the next topic we'd like to talk about is, since we use the pipeline in TCP as well, and the underlying channel is unreliable as well. So there's always a timer for TCP when you transmit a packet from the sender to receiver. So you have to set up a proper timer. Okay, so right here, when the sender and the receiver, if they send a very small packet, okay, the round trip time is something like this. So basically, when you send a data packet from sender and trying to receive a packet from trying to receive acknowledgement from the receiver, the timer you set up right here, right? There should be a timer right here. The timer should be larger than RTT, round trip time, because it's very obvious, right? So, but you know, there are lots of routers between sender and receiver. So we don't know what is the transmission delay. We don't know what is the queuing delay, what is the processing delay, and we don't even cannot estimate what is the transmission delay or propagation delay between the S and R, because there are a lot of routers, right? So RTT varies. So when we set up the timer, we should have some algorithm or some method to estimate the current RTT, and we will set a timer which is longer than the RTT that we estimate, right? So if the timer is too short, okay, there will be some unnecessary retransmissions, because if the timer is too short, maybe the ACK is on its way back to the sender, right? But you set a short timeout, so unnecessary retransmission is possible. But if you set a very long timeout, your performance will be very poor, because the sender need to wait a long time to wait the timeout. So the sender will be slow reaction to segment loss. So it is a very essential problem to how do we estimate the RTT, and how do we define a proper timer based on the RTT. So here it is. Okay, for sender, we can always send a small packet from the sender to receiver, trying to sample what is the current RTT between the sender and the receiver. So here is an example that the x-axis is the time. Okay, so maybe for a few seconds we send a probe packet from the sender to receiver, and the y-axis is the RTT time measured by the sender. So you can see that because the routers, the buffer size of the router, the queuing delay, the lots of different delays, they varies, right? So you can see that the sampled RTT, which is the blue dot, okay, sometimes it's lower than 200 milliseconds, sometimes it's even higher than 300 milliseconds, right? However, we can use a very simple way right here from the statistics. We can do exponential weighted movement average, EWMA. I believe you know what is it. I believe you learned it in statistics classes. Okay, so basically we choose a simple alpha value, which is 0.125 right here, for example. So you can do some average to calculate the estimated RTT, which is the red color right here, the pink color right here. And because it is some kind of average, right? So basically half of the simple RTT is below the estimated RTT, and the other half of the RTT is larger than the RTT. So basically it is just an estimation of the current RTT, and it varies as we know. So we should set up we should have a longer timer, okay, which is larger than the simple RTT and estimate RTT. So right here we have another. Right here is that here, the estimate RTT is the current moving average of your sample RTT right here, right? So basically, we would like to add some safety margin right here. So that is the timer interval we set for the TCP packet, okay? And the safety margin, how do we calculate that safety margin? It's right here. It is also sampled. It is also an estimation, okay? So basically, you can take a look at this part, okay? The green part, okay? Sample RTT abstract estimate RTT, and it is the absolute value, right? So basically, it is this part. No matter which one is larger, okay? So the green arrows right here, those are the absolute value we calculate, right? So basically, we would like to know what is the average of this arrows between sample RTT and estimate RTT. So basically, we have a value, okay? We have a moving average value of these green lines, green arrows right here. So that is here. And we times it with a beta value, which is typically 1/4. Okay, and again, it is a form of moving average. So that we know that the average, we know the average arrow between the sample RTT and the estimate RTT, but the average is calculated by exponential weighted moving average. Okay, so we have a lot of arrows can be calculated from here. And then we give it 4 times arrows, DEV-RTT, which make it a safety margin, so that we use this value as the timeout interval. Okay, as a timeout interval. So in this case, we can set up the we can set up the timer. Okay. We will talk about timer a little bit later, okay? So let's take a look at the TCP sender. Okay, we have a finite state machine right here, but it is an oversimplified one, okay? We simply just take a look at the event right here, okay? The review of those events, okay? TCP sender, when TCP sender receive a data from application, that means it receives some MSG. So the TCP sender will create segment with the current sequence number, right? As we mentioned before, the sequence number right here is the byte string number of the first byte in the segment, right? And the TCP sender will send the packet out. But meanwhile, the TCP sender will start a timer, okay? If not already running, that means because TCP has a window as well, so it only set the timer for right here. It only set the timer for oldest unacted segment. So if you remember those when we talk about pipeline, right? So again, TCP sender is very similar to the pipeline we introduced before. And here, there should be a timer for the very first yellow segment, which is the oldest unacted segment right here. Okay? So the current, the expiration interval, the timer right here is the timeout interval, which we calculated before, right? And at the right-hand side, okay, if the timer times out, and it will retransmit the segment that caused the timeout, which is exactly the first yellow segment in the window, and restart the timer. Remember that TCP is not go back and is not selective repeat. It only set the timer on the first segment. Okay, so it will only retransmit the segment that caused timeout and restart the timer. Okay, it will not retransmit all the packet. It will not set an individual timer for all the yellow segment. No, only one timer. Okay. And if the sender receive an ACK, if ACK acknowledges previous on ACK segment, which means it ACKs the previous ACK, which is the green ones. Oh, sorry. If the ACK acknowledges the previous on ACK segment, which is the yellow ones, okay, then update what is known to be ACKed, and restart the time. Start a timer if there is still yellow segment. Okay, and you have to. I think you have to write something right here. Is that TCP uses cumulated ACK. So if the current ACK the second yellow segment, and the window will move directly to the third one, right? As we mentioned before, if it acts this one, and these two segment will be green one right now, and we move because TCP use cumulative ACK. Okay, so make sure you remember all the things. And right here we have TCP finite state machine. So let's take a look at this one. Although it is an oversimplified one, but I think it is good enough for you to understand the entire operation of TCP. So right here again, we have the initial state. So the state number one is that when we start a TCP connection, okay, we have to right here, we have to set the send base and the next sequence number to initial sequence number. Basically, ideally, conceptually, it should be 0, right? Because it is the 0, the very first sequence number you like to use. But actually, it is a random number chosen by the sender, and we will talk about how this number operate. Okay, basically, conceptually, you can think, okay, it is 0. I mean, it is the initial value. Okay, the send base is 0, and next sequence number is 0. But actually, it is a random number. But the sender and receiver will know that random number will represent 0, sequence number 0. Okay, so that is the first one. And the second one, when the data received from the application above, that means message comes. Okay, so we create the segment by using the next sequence number. Okay, we pass the segment to the IP, means we send the segment out. Okay, you have to notice that the next sequence number now update to sequence number plus the length of the data, right? Because currently you send the data, for example, the length is 100 bytes, and your next expected sequence number would be current sequence number plus 100. Make sure you understand that in TCP, we all the time we use bytes as the unit to calculate the sequence, the next sequence number. Okay. So this one means if it is the very first yellow segment in your window, then you have to set up your timer for the segment you send out, right? So third one is right here. If timeouts, okay, timeout. Since the timer is on the very first yellow segment, so you need to retransmit not yet act segment with smallest sequence number. It simply means the first yellow segment. Okay, and you have to restart the timer. Okay, that is number 3. And number 4, as a sender, when you receive an ACK, then you have to parse the ACK packet and get the Y value. The Y value right here is the sequence number written in the ACK packet. Okay, so it indicates the next expected number expected by the receiver. Okay, so and you can see that we have two. There's right here. If the next expected sequence number sent by the receiver and it is larger than send base, okay, send base is right here, right? Send base is right here. If Y is larger, that means Y is in the window. Okay, Y is in the window, so that is means in the window. Sometimes, as a sender, you might receive an ACK packet which is right here. That means it is a duplicate ACK. It is an old ACK. So when, as a sender, when you receive such kind of ACK, you simply just ignore it. Okay, because you already know you received the packet because it is a green one. So you already know the ACK has been received by yourself previously. Okay, so that simply means if Y larger than send base, that means if you receive your new ACK and it is in a window, then you move your send base to Y. That means you move the window, right? Move the window because TCP use cumulative ACK, so you can directly move to somewhere. For example, somewhere here. For example, if you receive an ACK right here, right? So you can directly move your window to the next segment. Okay, so that is. And the red one means if there are currently not yet a segment. That means if you move your window and there is still yellow packet in your new window, then you start a timer. It means it has yellow. Otherwise, that means when you move your window back to some position and there has no yellow packet, there will be all blue packets, then you simply just start the timer because there's no yellow packet in your window. You don't have to set up a timer. So that is the simplified TCP sender. And you can see that it only control the retransmission only controlled by the timer at step number 3. Right? So let's take a look at the actual example. Okay? When host A send packet to host B and the current sequence number is 92 and 8 bytes of data is included in this specific packet. So basically we know that since there are 8 bytes, right? So the index should be 92 to 99. In total, there are 8 bytes. Okay, so when packet arrives at host B, and host B will send ACK 100 back to the sender because it expects the next sequence number will be 100 because it already received all the packets, all the data before 100. So if this specific packet, this specific ACK get lost, so the timer time out and it will retransmit the packet 92 and include the exactly same 8 byte of data and so on and so forth. That is the left hand side. That is the easy one to comprehend. Okay, at the right hand side, okay, because of pipeline, host A sent 2 data packet to host B. Okay, sequence number 92 include 8 bytes of data indexed by 92 to 99, and the next packet is sequence number is 100 and it includes 20 byte back data, so its index is 100 to 119. Okay, and of course we set up a timer for the oldest on ACK packet, so this right here, but that is a late ACK, right? That is a late egg. So at this moment T2, at this moment T2, timer times up, timer time up. So host A will resend the packet sequence 92. It's right here. But as for host A, okay, it will receive the late egg right here at T3, and at T4 is get the egg 120. Okay, and at T5 right here. Okay, and you can see that at host B right here, when B received the retransmission, right? That is the read. When B get the retransmission, okay, it will directly send cumulative egg for 120, right? Because at this moment, it already gets egg 120, and at this moment, it still sends egg 120. So that is more simpler for the host B to do such kind of acknowledgement. It simply just use cumulative egg to specify what is the byte received by the receiver. Okay, we don't have individual egg right here. TCP use cumulative egg. Okay, right here it is the same right here. And for example, if the egg 100 get lost, it's okay because we have another cumulative egg 120. So host A will get the egg and say, okay, all the packet before 120 will be is safely received by host B. So host A can continuously send the next packet from sequence number 120, and so on and so forth, so on and so forth. Okay, before we go to next topic, we'd like to talk about something which is a little bit which caused some performance degradation because of such kind of retransmission mechanism. Okay, take a look at this one. If we send a pipeline from A to B, right? But the second packet, sequence number 100, get lost. Okay, and you can see that that is the original egg 100 because it gets sequence number 92 and 8 bytes of data, right? So it will send egg. But the second packet right here get lost, and the third one, fourth one, and the fifth one, they received by the host B. Okay, but since TCP use cumulative egg, so at this moment, all the three packets can only send duplicated egg 100 3 times. For example, 3 times. Okay, think about one thing, that because those most of the time those packets are sent in a pipeline way, right? So basically, it is a little bit hard to only lose one packet within a pipeline. I mean, because these 4 packets sent to the pipeline consecutively, right? But you only lost one of them. It is a little bit the possibility of such kind of packet loss is a little bit low. Okay, but at this moment you receive 1 original egg and 3 original duplicate egg. That indicates that the channel might have something wrong, but not very severe, because all the 3 following packet arrives and all the 3 packets acknowledgement goes back to the host. So it is a hint that there's something wrong, but not that severe. Okay, so in this case we call it 3 duplicate case. Okay, 3 duplicate case. But you know the timer right here. The timeout will the timer is a little bit longer right here. So you have to wait until the second packet timeout, and then host A can retransmit the second packet, right? But we believe that it is a little bit inefficient because you have to wait until the timeout. So right here we have an idea that if you receive 3 duplicate egg, that means something is wrong, but not that severe. So in this case, we introduce a terminology called TCP fast retransmission. That means when you receive 3 duplicate egg at this moment, and you can simply just retransmit the packet. You don't have to wait until timer timeout, because those packets are sent from A to B very tightly, okay? And those eggs should send from B to A. It's the same, right? So there's maybe it is a very we have a very high possibility to believe that the packet get lost. So after you receive 3 duplicate, you can do TCP fast retransmission to transmit the packet. You don't have to wait until the timeout. So that will make the entire process communication more efficiently. Okay, that is one of the design of TCP we call fast retransmission. Okay, we'll stop right here, and we'll go. We will talk about the fast retransmission in the next hour. Okay, so we simply just stop right here. We just want to give you an idea that you can add a lot of different mechanisms on TCP to make the performance even higher, even better than the old version of TCP. Okay, and fast retransmission is one of the mechanisms that very important. Okay, we stop right here.